Welcome to the course Theory of Computation. This is one of the very important subject for every computer scientist. Actually, on going to this course Theory of Computation, you will come to know the capability of your computer and you will come to know that how computation is done and what is the notion of computation. So for solving any problem, you know that if you have some problem, you need to formulate the solution of that problem. And for solving any problems, you have some input. And for the input, actually, what you need to do, if you have the input, then you need to write some computational procedure, means you need to write some algorithm, you need to write some statements or sequence of instructions, you can say, which can be used for transforming the input into the output. So you have written the statements of your algorithm, and on going to the statements one by one based on the input, actually you are marching toward the solution. So every statement on execution, once your algorithm is executed, every statement is going to receive some information, and on behalf of the input information, it is going to do some computation, and the whatever the output is produced, that can become the input for the next statement. And in this way you are marching one by one, line by line, statement by statement, you are marching toward the solution. So here you have the computational procedure or algorithm, means the particular model of computation you have. Here you have the model of computation, and this computational procedure is responsible for transforming the input into the form of output. So this is the computation. Actually, you are having the input and you are transforming this input into the form of output, and this is the process of transforming the information. So your machine is going to compute, and once you are executing this algorithm, then you have the output. So this is the computation. Actually, computation, you should not mean just doing the mathematics or mathematical computation. Whatever you are going to execute with the help of your computer, everything is computation. In the field theory of computation, this is one of the branch in theoretical computer science, and the theory of computation deals with what problems we can solve on a model of computation using an algorithm, how efficiently you can solve, or to what degree. So here you will come to know that what problems you can solve. While going to this course theory of computation, actually you will come to know that what problems you can solve using the model of computation on a model of some particular model of computation using the algorithm, or how efficiently you can solve. This is also very important. How efficiently you can solve the problems. There may be some problem for which you require large number of computer resources, or you may need to find the you may wait for long time for getting the responses. So you will come to know that how efficiently you can solve the problems, and whether you are able to solve every problems or not. So in this particular course, actually, while going to in this course, actually you will come to know that there are there even you have the much computing power in your desktop, but still you are not able to solve every problem efficiently. And moreover, there are some problems for which you may not have the program, you cannot write the program, or you cannot write the algorithm of any time complexity. In the field theory of computation, generally you need, there are three major branches. We have the three major branches here. One is you have the automata theory. Automata theory is the study of abstract machines and automata, and, and the computational problems you are going to solve using them. So you will in this course, actually you are going to learn the number of abstract machines, we will start from the basic abstract machine, which we say that the model of computation. We start with the finite automata, which is the basic model of computation. Then we go for the push down automata. Then we, on generalization of the push down automata, we will get more powerful machine, which is the linear bounded automata. And then finally, actually, you will move to the powerful model of computation, which is the Turing machine. And here, these are the abstract machines you are going to study in this particular theory of computation here. Formal languages are closely related with the automata theory. And here we are going to study the 4 classes of language and their associated grammars. So here the word formal actually refers that you have the language, and in the language we have the set of sentences, or you can say that we have the strings, set of strings. So if you are having the set of sentences, then how would you know that what is the structure of that sentences? Means how you can construct. If somebody gives you the a new sentence, and he may be interested to verify whether this particular sentence is from the given language or not, then you should be able to verify by using the rules. And such rules, we say that the rules of grammar. So if you are able to explicitly define how you are going to construct the sentence of the language for each and every sentence of the language, or you have the notion that okay, how the sentences are formed, then actually we can say that okay, this is the formal languages. So here we have actually the 4 classes of language. The the 4 classes of language start we are going to study here, and we have their expressive associated grammars. You know, in this formal language actually, for every classes of language, we have the abstract device, we have the model of computation for particular class of languages. And so here actually you will come to know that which device, what is the accepting device for particular classes of language. And for more complex language, for more expressive grammars, you will have some more powerful machine, and the grammar which is less expressive, you will have the simple model of computation. Okay. Now, if you have to go for the computability theory, then actually you need to find the answer that what can be computed, or you can say can computer solve any problem given enough time and disk space. Time and disk space. So computability theory says that the what function you can compute and which function you can compute and which you cannot compute. So can computer solve any problem? You will have the notion that can computer solve any problems, even you are going to provide the enough time and disk space. The computational complexity, when you go for this branch, computational complexity theory, then actually you will come to know that how efficiently you can solve your problems, or how fast you can solve your problems. Actually, what you are required to do at this time, you need to find the computational judgment of your problem. So you should know the computational behavior of your algorithms, or you have provided the solution, and whatever the algorithm you have provided for solving the problem, you need to know the computational behavior of your problem. Means you need to know what are the resources your algorithm will take. Some algorithm may take more number of resources. Some algorithm may take less number of resources, and some may terminate in reasonable time, and some algorithm may not terminate even for some large input size. So if your algorithm is not going to terminate for some particular input, it may be busy with the computation, then actually you are not able to find the output, and the problems becomes intractable. So in case of the computational complexity theory, you will come to know that how fast you are able to solve the problems. On behalf of the input, what is the performance of your algorithm? Means you need to specify your best situation for your solutions. Means if everything is in favor of your algorithm, then what is the best time, what is the minimum time you require for your problems, to solve the problems. Or if the input is not in favor of your algorithm, then what is the maximum amount of CPU time your algorithm requires? You have to analyze. And on behalf of that, actually, you will come to know that in which computational class your problems comes. So basically, in computer science, we have the four computational class: class P, class NP, class NP complete, and NP hard. If the problems are in the NP complete, NP complete, or you have the NP hard, then really you have to think for the for the problems, because the problems which are in NP complete or NP hard, they are really hard problems, and for sufficiently large input size, you may not be able to find the answers for some particular input, and the problems becomes undecidable. So actually, the job of computer scientist is not to find the solution of some problem. Your objective is to obtain the efficient solutions. Then because for a small input size, every problem is solvable. But once the input size increases, then we have the problem. We need to think the particular model of computation. Then actually you need to use your experience. You can, whatever you have the experience, whatever you have studied the different computation models, whatever you have the different algorithm, on the basis of that, actually you can think whether which which scheme or which model of computation is suitable for solving that problem. So computational complexity theory is one of the very important, as for solving one, as you know that for solving any one problems, you may have number of formulations. You can number of ways you can solve the problems. Out of these number of ways, which solution is efficient, you have to know. And for knowing that which one is efficient, you have to determine the computational behavior of your algorithm. And on going through the computational behavior of your algorithm, actually you will be able to tell that okay, whether this problem is in the NP group or whether this problem in the NP hard group. In computer science, you just for the time being you just believe that the problem which are NP hard, they are intractable problem. Means for some input, they your computer goes to the infinite loop and you are not able to get the answers, and hence the problem becomes intractable. And you can say that if you don't know the answer for some particular input, then this is the undecidable problems. So computational complexity theory is one of the one of the very important and very crucial for every computer scientist. In the theory of computation, we will discuss the Turing machine. At the time of Turing machine, actually you will come to know that some problems are undecidable, and even there are some problems for which you don't have the algorithms of any time complexity. So you will come to know the nature of the problem. You will know the complexity of your problems, but how to determine the complexity and how to design the algorithms, how to compute the resources needed by the algorithm. You will find more details in the course design and analysis of algorithm. So the biggest question is, what problems can a computer solve? So say the answer The answer is not all problems. Not all problems. So consider this program. This is very simple C program, and you have the input n is the integer, and we assume that n is greater than 1. Okay, and we have the control part here, and it says that while n is not equal to 1, if n is not equal to 1 means whenever this condition is true, n not equal to 1, you have entered to the body. This is the body of the. So what you are going to do, you are checking whether n is even or not, and if it is even, then you are dividing by 2. If it is odd, then actually you are going to multiply the number with 3 and you are adding 1. 3 into n plus 1, and then the loop goes. So for example, if you see that if you are going to give the input n, which n is equal to 17, if you have the 17, if you supply n, then see that it is not equal to 1. Yes, so and also it is not even, so you are going to execute this part. So 17 multiplied by 3 plus 1, so this becomes 52. So n becomes now 52. Now again, if you go for this control part, then it is not equal to 1 and this is even, so you are going to divide the 52 by 2 and hence it becomes 26. So you have 26. Now again, it is not equal to 1 and it is even, 26 is even, so you are dividing by 2 and you have 13. Now 13 is not equal to 1 and 13 is not even, it is odd. So 13 multiplied by 3 plus 1, the answer becomes 40. So you have the 40 now. Now n becomes 40. Now n is not equal to 1 and it is even, so you are going to divide the n by 2, means 40 by 2, and you are getting the answer 20. And 20 is still not equal to 1, n is 20, it is not equal to 1, and 20 is even, so you are dividing by 2 and you are getting the answer 10, like this. And 10 is even again, and you are going to divide by 2 and you are getting the 5. N is not equal to 1 and it is even, so 5 multiplied by 3 plus 1 and this will become 16. Now 16 is even and hence you have to divide by 2 and it will become 8. Now this is the situation. Once it is 8, it is not equal to 1 and then it goes to the inside of the loop, and n is 8 here and you are going to divide by 2, so it will become 4. And again 4 is even, so you are going to divide by 2 and it will become 2. So once it is 2, it is also even, you are going to divide by 2 and it will become 1. Once it will become 1, now n becomes 1. So this says that while n not equal to 1, this is not true now. So if it is not true, then you are not going to enter to the body and your algorithm stops. This is stop. So see that for the n which is 17, for n is equal to 17, your algorithm stops. Now you may have the question that whether this terminates for all possible inputs, whether this program will terminate for all possible inputs. So how you can check? So what you need to do, you have to take the inputs one by one and you check whether your algorithm terminates or not. So you can give input anything, and n can be anything, whether it is 100 or n can be 1000 or n can be sufficiently large. So what you need to do, you have to check for every n whether this program will terminate or not, and see that there is no way to check because n can be anything, and there is no way to check whether this program will terminate for all possible inputs, and hence verification of the correctness of the program is impossible. Never think that the program which takes more time or program which goes to the infinite loop, they are complex program. Very simple programs can become the difficult on some input size. Depends on the input size. So very simple problems can become very difficult. Okay. So as we have seen that in the theory of computation is the branch which deals with what problems we can solve and what problems we cannot solve. So we are talking about the computation, and the word computation is coined after the invention of the Turing machine. So during 1936, Turing machine is invented by the scientist Alan Turing. And he was the mathematician. Alan Turing was the mathematician. Turing machine is considered as the general model of computation. And this is the powerful model of computation. In fact, any algorithmic procedure, if you can solve, or a team can solve, or some machine can solve, the same problems can also be solved with the help of Turing machine. If you are not able to solve the problem, means the Turing machine is not able to solve the problems. Decidability says that whether the problem is decidable or whether the problem is not decidable. If for some input, if your algorithm goes to the infinite loop, if your Turing machine is busy with the computations and it is not going to produce the output, means you don't know what is the answer and the problem becomes undecidable. Then halting problem is also one popular problem in the Turing machine. It says that if you are whether your Turing machine will halt for some given input or not. During 1940s and 1950s, the simplest model of computation is discussed, which we say the finite automata. So during 1940s and 1940s to 1950s, we have the basic model of computation, which is finite automata. Okay. And in this year, during 1950s, the Chomsky has also given the hierarchy, which is known as the Chomsky hierarchy of formal languages. And on going to the Chomsky hierarchy, actually, you will come to know that the classes of languages. So during 1950s, Chomsky has classified the languages into the four classes. One is the regular language, other class is the context-free language, context-sensitive language, and you have the recursively enumerable language. So for accepting the regular language, we have the basic model of computation, and once you go down from here to here, once you go down, these languages are much expressive, means the grammars of these languages are much expressive, and hence you need the powerful model of computation for accepting the recursively enumerable language, which is the Turing machine. During 1969, Cook introduces intractable problems, or you can say NP-hard problems. NP-hard problems are really the challenging problems, and which becomes the active fields of research to formulate the efficient solutions for such NP-hard problems. During 1970s, actually, the modern computer science is born actually, and we have the concept of the compilers, computational complexity theories evolved. So now you come to know that the course theory of computation is very, very important for every computer scientist. And here in this particular course, very easily you will learn the concepts one by one. We will start from the formal languages, then we go for the Chomsky hierarchy, means you will see the classes of languages and classes of associated grammars, and you will come to know that for a particular class of language you have the accepting devices, which can be finite automata, or sometimes you will have the Turing machines. So this is our ultimate, this is the objectives. We have to march towards the, starting from the basic model of computation, finite automata, we have to reach to the general model of computation, which is the Turing machine. So I wish you all the best for learning this course. Enjoy your journey.